Welcome to the third session of AC and DC motors. In this session, we will be discussing about motor torque, especially starting torque of an induction motor and the influence of rotor resistance on the motor torque. So in detail about the classic graphical representation of the torque current against the speed or the slip, and how these reactance and the rotor resistance influence on the motor torque, especially on the starting torque and the running torque, and how we can compromise this torque requirement, starting torque as well as the running torque, with the use of dual cage induction motors and with the use of wound rotor motors. So let's begin. Just to have a brief introduction with the squirrel cage induction motor, in this diagram we can see, in this left most diagram that we can see, you have the stator winding. There is a three-phase supply, and meanwhile in this middle, we call it the rotor. We can highlight this the green copper bars. These are the copper conductors, but which forms a spiral cage, as in this rightmost diagram. These each conductor bus making with the end rings, it's make a squirrel cage, which is in between the stator winding as the middle diagram. So you can see there are the windings of the stator winding. These windings will create rotating magnetic fields as they are supplied with three-phase AC supply. This rotating magnetic field will cause to induce some EMF in these rotor bars. Then the current which flows in this rotor bar will create a magnetic force, magnetic field also, and these two magnetic field interaction from the stator magnetic field and the rotor magnetic field. Then this reaction will cause a torque to develop in the rotor, which cause the motor to turn. Actually, for these basics, you can refer my first video and the second video. So in detail, I have discussed about the starting of motor and the construction and the other basic requirements, basic principles of the motors. So if we dig into further, then we can see this diagram. These two are the stator winding. One phase, two poles I have taken. Suppose in this positive half of the supply, let's say if this is creating north pole and this one is south pole, in next negative half cycle, this will alternate. That means this one become north and this one will be south. Anyway, there will be a magnetic field acting from north to south. And this magnetic field, then this loop, ABCD loop, which is the squirrel cage section, one loop of the conductor bars, that will subject to the magnetic field and induce one EMF that will cause the force from here on BZ to upward direction, on the AB to downward direction, which will cause a couple. Then the motor will start, the rotor will start to turn. And even though in squirrel cage induction motor, apparently we don't have any coil, this copper conductor arrangement in a squirrel cage, we can consider this as a coil. It has a resistance as well as a reactance. So the resistance is normally a fixed value. As we know, if you measure at the ends, the ohmic value, it will be constant. But the reactance, which is XL, is depend on the frequency of the induced EMF, which is flown in this loop, and also the inductance of the coil. So this induced EMF frequency, which is proportional to the slip frequency, or maybe we can assume that is we can name it as a flux cutting rate or flux cutting rate frequency. So from the beginning, the flux cutting rate will be maximum, or else the slip frequency will be maximum. In other words, the difference between synchronous speed or the stator rotating magnetic field and the rotor speed. From the beginning, the rotor will stationary. So then that case, the velocity between these two will be maximum. So we call it as the reference velocity will be maximum. So that's why we call it the slip frequencies at its maximum. So from the beginning, your reactance will be very high. That's why your power factor in induction motor when starting, it's very high. Right. So then let's see what are the other principal parameters which influence on the torque of the motor. So to create the torque, the force, there should be current flow and some magnetic field create. So this current flow, of course, it is depend on the flux phi, which is of the stator flux, and the rotor resistance, and there is a rotor reactance also influencing on that. Here we go. This is the equation for the torque. The torque is proportional to your phi, that is the stator flux, and the rotor current, and the cos theta. The cos theta is the angle between your stator flux and the induced current on the rotor. Or else this cos theta you can see, you can name it as the power factor of the motor. As I mentioned earlier, the rotor reactance varies with the cutting rate, which is depend on the rotor speed. So the power factor is varying from stationary condition to the full speed condition. Starting the lowest power factor, and the power factor will increase as the rotor gains speed. This is the diagram or characteristic curve of a motor, the torque and the current. This y-axis represents the current and this axis represents the torque. The x-axis is the rotor speed. This dashed line, it is the load torque curve. That means if some load, suppose a pump connected to the motor, the load requirement, the required torque from the load, this is it represents from this dashed line. And the blue one is the motor torque characteristic curve, whereas this red one is the current, the motor current. So there are two different characteristics we can see. First, we will look into the current characteristic. From the beginning, it takes 7 times full load current almost. Its full load current somewhere remain here, somewhere here, and it takes 7 times of its full load current. This is the full load current. The working operating point, let's say it is here. So this is the point. So this is the operating current, full load current at that point. So that is 7 times. Because from the beginning, as the rotor stationary, flux cutting rate will be maximum. So the maximum current will induce in the rotor. That's why the highest current is taking place. As this equation, if the current is high, your torque should be maximum. As the current is maximum, your torque should be maximum. But it is not at its maximum. You can see the torque is maximum at somewhere around 90%, 80 to 90%. At the beginning, it is not maximum. The reason behind is that cos theta value. From the beginning of starting, your XL value will be very high. Because of this 2 phi FL, as your frequency, flux cutting frequency is very, very high, then your XL value will be very high. Then your cos theta value will be very less. As theta increases, cos theta decreases. So this multiplication will give you somewhere around about 3 times, let's say, full load torque, some kind of this much of torque for starting. But as the motor gains speed, flux cutting rate gradually will decreases. Same as your XL value will be decreases. So as a summation, that curve will behave in this manner, where at its 90% of load, it will give its maximum torque and your current will reduces. As the rotor reach its synchronous speed of the stator, there won't be any cutting, magnetic field cutting or flux cutting. So then there will be no any induced EMF in the rotor. So that's why the current is zero. So the always induction motor is not, it will not be run at 100%. It will be run with some slip. So here around less than 3% normally we are running. So some slip will be always there. So this is the operating point. So as per this equation, it is well clear now the rotor resistance is directly involved with the cos theta. Thus, it is directly related to your torque. For examination purpose, this diagram I will just explain the same one. The torque curve and the current curve is there. So the rotor speed from 0 to 100% by this green line you can see, and the slip, it is inverse of this rotor speed. From the beginning, the slip is 100%. When it is at 100% speed, the slip is 0. Right? So if this in this curve, we can see if the motor operating point is this part, this is the full load operating current, and this is the full load operating torque. This will be the torque, the slip. And in this diagram, for this point of this torque curve, we call locked rotor torque. And this point pull up torque, and the peak one we call breakdown torque. Then suppose let's have a look on the voltage variation, reduced voltage variation effect on the motor torque and the current. Suppose this green line is the torque, load torque demand. If you connect a pump or couple a load, then this is the torque demand. Suppose this is full load torque. Then you supply your, let's say motor rating is 440 volts. So you supply your full load, full voltage. Then your curve will behave in this way. So this is full load condition. So your motor torque and the motor current will behave in this way. At next starting, we will try to start at lower, reduced voltage, let's say 380 volts. So in that case, your current will lower because as there is no voltage, it will draw less current. Because of the less current, it will not be able to produce the same torque as previous. So the torque curve also will fall below. Current also fall below, and the torque also fall below. And then if further reduces, let's say 300 volts, again it moves further down. So these will be the reduced voltage effect of the torque and motor current. Again, almost similar diagram here, speed versus slip. You can see this is the normal operating slip, this point. Suppose in that some case, due to the load torque increases. Suppose when you are filling a pump, the tank with the pump, as the head increases, your load will increase gradually. So in that case, the load on the rotor will increases. So it will cause slip to increase. So let's say as the torque increases, load torque increases, your slip increases to this point. Now the operating point will shift to here. In this case, as the slip increases, then the flux cutting rate will be higher. So that induction will be higher. Then you will draw higher current. Thus, your torque developed from the motor will be increased. So motor will supply the additional torque which is drawn from the load. And in exams, if they ask to draw the torque versus slip curve, this will be the behavior. It is something similar. If you draw your y-axis here, and if you consider the mirror image, so that will be torque and slip curve. That is the mirror image of this one. Here, this equation is the slip equation. Synchronous, this rotor speed will be minus from synchronous speed and divided by synchronous speed and multiply by 100%. So that will be the slip percentage. Next, now as we discussed, we know the torque. Starting torque of a motor, actually the relationship basically we can take as a constant, this K constant. And then we can consider this rotor resistance and the rotor reactance. So the starting torque is a function of basically rotor resistance. It's proportional to rotor resistance. If you want to increase the rotor resistance, then you have to increase the if you want to increase the rotor torque, starting torque, then you have to increase the rotor resistance. Normal induction motor, squirrel cage induction motor, basic disadvantage is they are having very much less starting torque compared to their full load torque. So to improve that one, we have to increase. If we can increase the rotor resistance, then you can increase the starting torque. But unfortunately, if you want to increase the rotor resistance, then there will be another problem, because then there will be some resistance to current flow in your conductor bus. Then the running torque will be affected. So then your running performance will be lowered, retarded. Let's take this diagram. You see there are three graphs. The first one is having the lowest starting torque because it's having the lowest resistance, R1. As the rotor resistance is lower, the starting torque is lower, but it has considerable higher torque, running torque. The second one, this one, it has the R2, rotor resistance is something higher, so it has good starting performance. Suppose your operating point is in this lies on this line. In that case, if you draw right here, let's say this is your operating point. Okay. If you draw here, okay, this is the operating point. You can see in first case, your operating torque is very high. But in second case, your starting torque is high, but your operating torque is less. In third case, your starting torque almost equal to your full load, full torque, the available full torque developed from the motor, but your operating torque is somewhat less. So in this case, it's clear blindly increasing your rotor resistance would not give the motor performance. So we have to find some solution to elevate the starting torque as well as to maintain the running or operating torque. So to achieve that, we have two techniques, basic techniques. The first one is dual cage induction motors. What we have discussed so far is single cage induction motor. That means only one squirrel cage apparently we would see. But in dual cage, there will be two squirrel cage, one beneath the other, like parallel fixing something. There will be two cages in the same rotor arrangement. And the other one is the wound rotor technique. So first one will go to the double cage motor. This first diagram, it is a single cage normal rotor. These are the rotor bars. But we can modify this one to have two separate conductor bars. This one, the top one, the outer cage creating, and this one will be the inner cage. This is a cross section of the rotor. So let's consider the first one, the outer cage, it having the higher resistance. That is how it's designed. It will have the higher resistance and it will have a lower reactance value. But inner cage, it has lower resistance but very high reactance. So from the beginning at starting, due to very high reactance, there won't be much current flow in the inner conductor bars. So it will not support, giving any support to create the torque. Very minimum effort it will support. But mostly in outer cage, as it has higher resistance and very less reactance value, then the current mostly will flow in outer cage and developing much more torque during starting. as the resistance is high, rotor resistance is high. But as the motor picking up speed, then your reactance value of the inner cage will get lowered. Thus, then the current induction of this inner cage will be much more, and it will contribute to supply the torque, the running torque. Then the combination of these two characteristics will give you elevated starting torque as well as very good running torque characteristic. There is another phenomena we call it skin effect. Skin effect also, from the beginning of starting, it will retard the current flow in the inner cage because of the restriction from the electron flow of the accumulated on the surface of the cylindrical space of the rotor. So this is the arrangement of a dual cage induction motor. This is the rotor. These are the inner conductor bars, and these round one are the outer cage. Cross section, these are inner, these are outer. So we can see clearly the characteristic inner cage, as it has lower resistance, starting torque is less, but running torque is high. Outer cage, starting torque is very high, but its running torque performance is less. Then the final outcome from these two, the dual cage, it gives very good starting characteristic as well as the running characteristic. So this is the principle behind the double cage rotor. And do not get confused this arrangement with the dual pole or dual wound rotors. Dual wound rotors, they have two separate stator windings. This one has two separate rotors. Rotors means same rotor but two squirrel cage arrangement. This one is one squirrel cage, the other one is the outer squirrel cage. Same rotor having two squirrel cage arrangements. Then the second method of improving the starting torque is wound rotor. Wound rotor, it has a stator and the rotor which is wound with copper coil, and it is connected to brush and the slip ring connector, and there won't be any current supply or voltage supply here, but it will drawn to somewhere with the external resistance band. From the beginning, for the beginning of starting, the resistance will be maximum, then the rotor resistance will be at its maximum, so the torque will be its maximum starting torque. But as gradually the rotor picking up speed, then there will be some arrangement to reduce the rotor resistance. External circuitry will be there as the rotor picking up speed, so the gradually the resistance will lower. When it's running to full speed, this resistance will be omit. Then this will act as an induction motor. Then there will be a current flow in the rotor, which gives the running performance also in good at good level. So this is the torque behavior of a motor. In this session, I will stop the discussion from here. Next, we will move to starting a method of the motors, and then the DC motors and other principles behind the motors. Hope that you have enjoyed the videos. Thank you very much for being with me, and please subscribe if you not subscribed yet. Yeah, see you.